Thank you very much. I would like, as is customary, the organizers of the meeting for inviting me to this workshop. I've actually learned a lot the last few days. So I should have updated most of my slides, but there were so many questions about classical integrability that I decided to not waste my time adding stuff that people already knew about. And I sort of enhanced, I think it's enhanced, but it's longer in any way. I don't know if it's better, but it's at least longer now. So there will be a long introduction, because I think in the title already there are maybe some concepts that I need to explain before I can actually explain something new. And I'm not talking about the ultradiscrete KdV equation, but in a sense I am. So let me start by explaining what exactly the problem is that I'm going to tell you about. So the talk is roughly based on this paper, which is, well, recent, not so recent. It's pre-COVID, so in that sense it's probably recent. So what do I mean by the ultradiscrete KdV equation? So this is just the title in a long version. It's an equation which we've seen under various forms. It's been discussed quite a number of times by Tsujimoto-san, by Sasuda-san, by other people as well, either in a Yang-Baxter form, in a tropical Yang-Baxter form, as a set of local relations. I think Sasuda-san mentioned that she doesn't like this form because it's non-local, but I'm going to treat this non-local equation. Now, it is an equation that is defined over the real numbers. So up to now, we've always heard about box and ball systems. So basically, the dependent variable, u, in a box and ball system only takes zeros and ones as values, but I'm not going to care about that. In the introductory part, I will care about zeros and ones, but after that, it will simply be real numbers. And I will impose certain boundary conditions and conditions on the initial value problem. So the boundary conditions, I'm trying to do this right now. I mean, all evolution, because of the non-locality in the equation, all evolution will be from your left to your right. Yes. And so I'm imposing boundary conditions on the left. So the values of the dependent variable only take zero values on the left boundary at infinity. And all information will move towards the right, and I'm only considering initial conditions that have finite mass. So even stronger, not only finite mass, but the initial conditions will always have finite support on the lattice. So that's the basic assumption. And that will ensure integrability in a very precise sense, in an inverse scattering sense. So that's the basic setup. Of course, if you restrict yourself to zeros and ones, I'm not going to spend a lot of time on this. I mean, we've heard this story now, I think 5 or 6 times at least this week. So you have a solitonic system, which was first discovered by Takahashi and Satsuma, and all evolution is, as I said, from your left to your right under this evolution rule, which is actually closed on zeros and ones, which is sort of, I mean, if you, it's not obvious. You have to check that it's actually closed, and the system only contains solitons. But any initial state simply decomposes into a train of solitons, and we've heard about that quite a lot. This is a picture for people who haven't seen the picture yet, but I think everybody knows the picture. You have 3 solitons going in, and after a number of time steps, 3 solitons coming out in the right sorted order. We haven't heard a lot about the phase shifts that these solitons incur, and that's actually, I mean, that was one of the interesting things in the original Takahashi-Satsuma paper. And basically, the phase shifts are described here. I'm not going to spend a lot of time on the phase shifts. I think there are more important things, but basically, the fast ones are pushed forward by the slower ones. The slower ones only feel their own masses, and the fast ones only feel the masses of the slower ones. That's the basic interaction rule. And these are some important, at least, well, not only historically, but important references. Of course, the original BBS reference, the original solution to first the periodic Cauchy problem was given in this paper. And then I think the original linearization using rigged configurations was, there's no proof in the paper by Takagi, but there's, well, at that point in time, an important conjecture about how the rigged configuration should be constructed using 1-0-0-1 elimination. The stuff that you talked about, Tsujimoto-san, during your last talk. Yes, so there were no proofs in that paper, but in that sense, it's probably the oldest paper on linearization in terms of what was called action angle variables. Now, in my talk, there will be action angle variables as well, which are much closer to the scattering problem, the inverse scattering problem for the continuous KdV equation. So That's what I hope to get to. Exactly, that's on this slide now. So this is what the main result of the paper by Takagi in 2005, that there is a systematic way, one, to construct a Young diagram and reading. And in that paper, he is not using the KKR bisection. That's exactly the point. He's using basically only 1, 0 and 0, 1 elimination. And the details on KKR were first appeared in this paper, which Kuniba-sensei also mentioned this morning, and the link to 1, 0 and 0, 1 elimination, that is something we did with Takei-san and John Nimmo quite a while ago. Now, of course, as I said, the equation is closed over 0 and 1 for the dependent variable, but that's sort of a, in my eyes, a fluke. Yes, it would be much more natural to discuss the evolution equation as an evolution equation of the real numbers. And that's what I'm getting to. But Hirota-sensei already did that kind of study over the integers. And I'll come to some interesting results that he obtained in this paper in 2009. And then I didn't mention them on the first slide, but with people in Paris, Basile Grammaticos, Alfred Ramani, we discussed a possible method of solving the Cauchy problem, first over the integers and then over the reals. But those were basically physics papers. There were no proofs. In the talk, there will be theorems, but there will be no proofs. The proofs will be, well, they're rather technical. I'm not going to spend time on proofs. The dependent variables will be real valued, not 0 and 1. Yes, the dependent ones. And you're still evolving on the Z2 lattice. Yes, that's the idea. So this is what I will explain, what this picture means. So basically, the red dots are an initial condition, finite support, and the blue line is actually a continuous function that describes the general solution to the Cauchy problem. And the main result that I want to explain is how to obtain this continuous function in the space variable and the time variable that basically interpolates the evolution of the initial condition over the real numbers in a unique way, in the sense of the Cauchy problem that we're trying to solve. Yes, and so this is a typical time evolution. Soliton coming out, but you see something that is non-solitonic. And so it's on repeat, but if you look carefully, you see a soliton coming out here, and then another soliton here, and then something that doesn't change shape. That simply moves at speed 1. So let me get to the next slide. I first have to recall some concepts on the original continuous KdV equation, because the picture you just saw, the moving picture, is very, very close to what people have observed a long time ago for continuous KdV. So continuous KdV, of course, everybody knows the form of the equation, has a Lax pair, and there's a scattering problem first, a direct scattering problem for the initial conditions, and then an inverse scattering problem to reconstruct the solution to the Cauchy problem, associated essentially with this ODE, which is a spectral value problem. And there are very important and quite severe conditions on the initial conditions to make the entire scheme work. So that is a recurring theme in the questions in several talks. What do you mean by integrability? Well, integrability of a PDE is, of course, subject to the initial condition or the initial value problem that you're thinking of. It's not simply a property of the equation. Of course, the equation has to have certain nice, I would say, algebraic properties. But you're not living in a vacuum. Of course, you have to impose conditions, boundary conditions, condition on the initial value problem. Otherwise, you cannot say what you mean by integrability. So under very strong conditions on the initial conditions, you can actually reconstruct the general solution for this kind of initial value problem on the real line. I'm only talking about initial value problems on the real line. And I mean, of course, this is a very classical and very well-known story. This eigenvalue problem, there's a finite simple discrete spectrum, and then there's a continuous spectrum. And I prefer to show a picture. This is also a picture that Tsujimoto-san showed in his first talk. This is, I'm not going to tell you how it was constructed, what the simulation is, I can tell you afterwards. But this is an evolution for the continuous KdV equation. So you have a right-going part that becomes a soliton. It's not quite yet a soliton, but probably now it is almost solitonic. And then you have a dispersive wave train going on. going out to the left. And then there's an interpolation. You can recognize some kind of an airy function here that interpolates between the dispersive part and the solitonic part. Now, that is a very old result, which goes back to Ablovitz and Seeger, beginning of the 70s. And so basically, this is the basic picture that is one of the claims I'm going to make, that you already saw in the ultradiscrete equation. In the ultradiscrete equation, there's a minimal speed of 1 going out to the right because of the way the equation is set up. So there's no left going path. So everything moves with at least speed 1 towards the right. But what you're seeing is exactly this. There are solitons with speeds greater than 1 coming out asymptotically, separating from the rest, and the rest simply is compressed into a block that moves constantly at speed 1. And that's what we saw in the first simulation. So there are an enormous amount of results on the scattering problem for KdV. I think the most famous formula, in a sense, describing the interaction between the solitons and the continuous spectrum is this one by Ablovitz and Kodama, which is quite old. And there's a first version of it in even an older paper. So the eigenvalues to the scattering problem are the discrete spectrum, and then you have to choose how to characterize the continuous spectrum. And of course, if you're purely solitonic for reflectionless potentials, you forget about the continuous spectrum, you only have solitons, and then the interaction rules are very, very simple. And basically interaction rules are given by the solitonic and soliton formula that Sugimoto-san showed for KdV, for the continuous one. But of course, if you have continuous spectrum, the continuous spectrum actually influences the solitons as well, and vice versa. So the lambdas describe the discrete solitonic spectrum. You can have right and left normalization constants for the eigenfunctions, and you can characterize the influence of the continuous spectrum in that sense. And then you can give a very nice and compact formula for the phase shifts incurred by any soliton that comes out of the initial value problem. There's an alternative, and in a sense, a nicer description of the same type of phase shift, which only uses the left normalization constant for the eigenfunctions in the spectral problem and a reflection coefficient. And the nice thing is that the reflection coefficient has exactly the same, well, a similar, it's not the same. It has also a very simple exponential time evolution under the Lax pair for KdV. And given these data, I'm not going to explain how that is done for the continuous case, but given these data for an initial condition that you start from, you can actually reconstruct the general solution to the Cauchy problem under the conditions that I described in the beginning. And there's also a very, very nice, this formula is not very well known, I think, for the solitonic interactions, simply characterized in terms of the discrete spectrum and the reflection coefficient. I think this formula is very, very interesting, but not a lot of, but it's not well known enough, I think. Okay, now how am I going to transpose this story, which is basically, it has to do with analysis? And how do you transpose that to the world of ultradiscrete equations? And that is, and probably I'll get shot down now by people, either in the audience or online, because it actually works because the integrability of KdV, even the continuous one, has more to do with algebraic properties, with vector transformations, or Darboux transformations in this case, than with pure analysis. There's a very remarkable theorem by Deft and Trubowitz in this extremely famous paper where they describe the inverse scattering on the line for KdV. And the statements concern what they call dressing and undressing transformations. So the statement is written down here, but basically, if you have one of these operators, it's the heat operator, but okay, with n bound states, if you choose an eigenvalue, or if you choose an eigenfunction corresponding to an eigenvalue that lies above the discrete spectrum, then you can actually dress the initial potential in the operator such that you create an extra bound state. That's the dressing statement. And now you can undress in the reverse way by choosing the highest eigenvalue and perform the same operation, take a bound state for that highest eigenvalue, and then do exactly the same transformation on the potential, and you take out one eigenvalue from the spectrum, from the discrete spectrum, without disturbing the rest of the spectrum. If you would choose any other eigenvalue, you would muck up the entire spectrum. It's crucial that you only take the highest eigenvalue to do the undressing. And now my claim is that this works exactly in the same way for discrete KdV and for ultra-discrete KdV. The only problem that is left then, when you realize that this actually works, is how to define a scattering problem for ultra-discrete KdV. So that's going to be the most important part of the talk. This is the beginning of the 90s. I was involved with basically John Nimmo. Well, there are these things that are the things that most people knew but were never written down and never attributed to somebody in particular. Like one of the neatest ways I know to derive discrete KdV is by basically taking the Darboux transformation for the potential version of KdV, continuous KdV, and simply look at the Bianchi permutation diagram for the Becklin transformation. And that is basically the discrete version of potential KdV. Yes. So you could say, in a sense, it was Bianchi who found it. But of course, it was only recognized at the end of the 80s. But who found this the first time? I heard it from many people. So it's basically. And so the type of problem I want to solve is this. If you're working on the reals, then why not choose an initial value, finite support, and just start from pi. And then the typical evolution will be something like this. After 3 time steps, you get a soliton that will not be shape preserving, because it will be moving with a crazy speed, 2 pi minus 1. So the speed of the soliton that comes out is no longer commensurate with the equal lattice spacing that you're doing, lattice spacing of 1. So you will have some kind of stroboscopic effect, and the soliton will never stop changing shape. It's not even periodic. And then you have a background coming out, which simply moves at speed 1. Of course, you can also describe interactions of solitons, a regular box and ball soliton, three ones in a row, with a big hole in the lattice, and out comes a soliton now with speed 3, integer speed, and that is now a fixed shape soliton. So this is basically the type of process I want to describe in detail. I'll skip this is not important. So this will be the algorithm. The algorithm basically boils down to the 2 theorems by Dave and Trubovich that I showed earlier. The algorithm basically boils down to dressing and undressing, or I should rephrase this. It boils down to undressing and then dressing. You start from an initial condition, for which I haven't shown you the scattering problem yet. I will do that on the next slide. You define basically an eigenvalue problem, and you solve a direct scattering problem for a given initial condition for the ultra-discrete KdV equation. And then once that problem is solved, you can use that information in the undressing version. You know exactly what the bound states are, and starting with the fastest soliton state, you start undressing the initial condition up to the point where there are no solitons left. Luckily enough, and that is a result due to Hirota sensei, a state for the ultra-discrete KdV equation that has no solitons simply translates at speed 1. So if you have an initial state that has no solitonic content, it simply translates with speed 1 towards the right. I'm sorry. And so you can easily write down an analytic solution. I mean, it's simply a translation of the initial state with speed 1 on the lattice. So you immediately write down a continuous function that will do that. And then you take that function, and there's a very precise algorithm, basically an ultra-discrete Darboux transformation, that allows you to use the information you had in the undressing phase, to use that to put all the solitons back in the right order, starting with the slowest one back to the faster one by an ultra-discrete dressing information. And then you get an explicit analytic expression for the solution to the Cauchy problem. That's the basic idea. So, okay, people are always asking me, do you have a lax pair for ultra-discrete KdV? Well, yes and no, because it's not a pair. Yes, so what you would like to call the lax pair, so this is again the equation, what you would like to call the lax pair is probably this equation, which is really an ultra-discrete version of the spectral problem for KdV, and then one of these two. Why do you need 4? Well, for people familiar with inverse scattering, you want to define something that, well, Yost functions. So at least the lax pair has to fix the asymptotic behavior for these Yost functions. Now, in the ultra-discrete world, since you're working on a strange semi-field, these equations can't really be solved in any precise sense. And an equation involving max operations does not necessarily have a unique solution. So if you simply take any 2 of these equations, you will never be able to determine the asymptotic behavior for a free problem. So you can try playing around with these equations, and the minimal set of equations that actually allows you to fix asymptotic behavior for the solutions to the scattering problem, the minimal setting always involves 4 equations. There are different ways of writing them, but you need at least 4 equations to actually do this. So this system is heavily overdetermined. But with less than this, it simply doesn't work. So what are the ingredients? You have a function that is now, I write a linear system, but it's linear, of course, in this semi-field. So by linear, I mean if you have 2 solutions to the system, then the maximum of the 2 is again a solution. Or you can add any constant to the solution. Again, it's a solution. It's linear in that sense. And there are basically 2 constants that have to be determined. Well, I can not now, but if you want, I can explain why there are 2. They're linked. If you have solitons, there's only 1 parameter. In the free problem, you have 2 parameters. So omega is really the spectral parameter. Omega will be the solitonic mass, the solitonic speed. And kappa is related to omega if you have solitons. So that's the idea. So this is basically, these are the equations I'm going to be discussing. So I have to make a small excursion to the discrete KdV equation, because there have been questions about integrability for discrete KdV. And we saw the Lax pair in Sugimoto-san's talk, but we didn't hear about inverse scattering for discrete KdV. So this is one way of writing discrete KdV. I think it's the same expression as in your talk. I wrote it slightly differently because this is a form that is ultra-discretizable. That's because you have no minus sign. And you could naively ultra-discretize this equation, but then you get stuck with an expression that has, well, it's not an evolution equation. It's the maximum of something equals the maximum of something else. And there's no way to evolve for generic initial conditions. For very special ones, it does evolve. But so if you're thinking of ultra-discretizing the discrete KdV equation, you have to go through the algorithm that Sugimoto-san explained, because this form is pretty useless. But there's a very nice Lax pair, which has all the properties you would expect of a Lax pair. It has a spectral parameter, which is the lambda. Delta is simply the parameter that appears in the equation. And beta is just notation that is very convenient. It's this expression of the deltas. And so this is a second order scattering problem, spectral problem, involving the spectral parameter. And then you have the deformation equation, which gives the time dependence of the eigenfunctions. It's exactly the same structure. The scattering problem, and I'm cheating a little bit, the scattering problem for potential discrete KdV has been solved in this paper by Butler and Joshi about 12 years ago. Now, going from the potential KdV equation to the KdV equation is very simple. So if you've solved the scattering problem for the potential version, then you can claim to have solved the scattering problem for KdV itself. The other way around, there are technicalities because you have to fix the boundary conditions then. But so in principle, the problem was solved 12 years ago using a slightly different version of the Lax pair, but essentially it's the same. There's one interesting thing, because people have been trying to do, well, scattering. There were a bunch of papers in the 70s up to the early 80s, scattering for this type of operator. But the problem is if you want to link that to discrete integrable systems, you can't do that with the regular L2 norm. It simply doesn't work because the L2 norm is not special for these integrable systems. So this is the norm you have to use for discrete KdV. It's not L2, it's strange. There's a gauge factor because the system is not self-adjoint explicitly, but the adjoint is gauge related to the original one. So it's almost self-adjoint. So that's why we have this crazy function here. But you see, it's not the regular L2 norm. So you can define a scattering problem that has then all the nice properties of having a finite and simple spectrum, but with respect to this norm for the eigenfunctions, for the bound states. Otherwise, it doesn't work. So that's a technical comment. This is also something we saw in at least 3 talks. I think this is the relation between the tau functions for discrete KdV and the solutions to discrete KdV. It's this quadri ratio, and the tau functions have to satisfy this bilinear equation, which will not be very important in the talk, but I have to use tau functions. So I can't not show this relation. Now, what is the discrete equivalent of the transformation of the potential that you saw in this theorem by Dave and Trubowitz? Well, it's this type of Darboux transformation. The statement is very simple. If you have 2 solutions phi and theta to this Lax pair for the same potential u, corresponding to different eigenvalues, mu and lambda, then this combination, this basically the ratio of two Wronskians, if you want, this combination will be a solution to the same set of equations, but for a transformed potential, which is this u tilde, which is basically, I mean, if you use theta to perform the transformation, then this will be the new potential, this u tilde, and this phi tilde will solve this Lax pair for this potential. Now, the transformations look complicated, especially this looks sort of, well, it has a nice form, but the transformation of the tau function is absolutely trivial. Transformation of the tau function is simply multiply the tau function by the eigenfunction you chose. And that's a very neat feature of the Darboux transformation in the continuous and in the discrete world, because it tells you that the transformation is the same, actually, for both discrete and continuous. So this is the Darboux transformation. Now, this will be, I'm sorry, this will be a dressing transformation in what comes next. How do you undress? Well, since the transformation of the tau function, I'm sorry, I keep doing this. Since the transformation of the tau function is very simple, you could simply divide the left-hand side by the same eigenfunction, and then you go back. But of course, you would like to have a similar statement that you can construct solutions to the Lax pair for the transformed problem. But essentially, it's the same idea. You basically take the inverse up to a gauge factor, basically adjoint. You take the inverse of the original eigenfunction used to dress your potential to define exactly the same Darboux transformation, and that way you undress. Now, this relation will be important because it's difficult to mimic this in the ultradiscrete world. Why am I saying this? Well, I'll explain later. It will be much more. It's not immediately visible on the explicit form of the equation, but yes, that's the only way to go about it. It's the same restriction. Okay, so now I'm going to go ultradiscrete. I'm not going to explain about the ultradiscrete limit. That was done again in at least 2 talks, but you can define some sort of a limiting operation that takes you from the discrete world to these equations on this semifield, max plus semifield. The quadri ratio expression for the u's in terms of tau functions now becomes this very simple difference relation. So these will be ultradiscrete tau functions which satisfy this relation which we saw this morning in Kuniwa-sensei's talk. And the original equation, the ultradiscrete KdV equation, its solution u is expressed in terms of solutions of this equation. And so you can perform a similar limiting procedure on the original Lax pair, but actually, how do you, well, the problem you have to solve is how do you overdetermine the system such that it becomes useful. And basically, this is the ultradiscrete limit of the discrete scattering problem. This is just its time update, where you've used an alternative form of this equation, which was obtained, I said, there's this naive, useless ultradiscretization where you write discrete KdV such that it only has plus signs, and then you say it's max equal max. Well, if you use that relation in here, you see you have a max of 2 quantities, then you can see that this is just the time update of that. Yes. So the second equation is just the time update of the first one. But the nice thing is that it only involves the potential u at one instant in time. And then I forget which one it is, probably this one. This is just the ultradiscrete limit of the deformation equation that defines the time evolution of the time evolution of the solution to the Lax pair. And this is something you can obtain by playing around with the first 3 equations. You have to get lucky to find this. And for solitonic states, this will be the definition of kappa. So kappa will be the minimum of 1 and the real spectral parameter. So what about Darboux transformations? Because of course I can't do any analysis. So the only tool that might be available is to use this, well, an ultradiscrete equivalent of the Dave Trubowitz dressing and undressing transformations. So I need ultradiscrete Darboux transformations. So do they exist? Well, for the tau function, since in the discrete world, simply multiplications, and I become summation, and everything seems perfect. But of course, everything breaks down at the level of the eigenfunction, because there you have a ratio of 2 Wronskians that you have to ultradiscretize, and there's simply no way to do that. So everything breaks down here at this level. So that is the problem that needs to be solved. So I mentioned the reason why I want to have 4 equations in my, it should be a better word than Lax pair. Yes, so the Lax quadruple or something. This is because of behaviors. So if you have the 3 problem, so you have a very large eigenvalue. So you might have solitons, but you're way above the discrete spectrum with the value of omega. Then this is the generic asymptotic behavior. Remember that I'm imposing 0 boundary conditions on your left. Yes, that is why of course, I can always renormalize. I can add any constant to the solution, but I'm normalizing on the left at 0, and then this is the asymptotic behavior on the right. That is for the generic free scattering problem. Now, if you have very special values of omega, which basically will be the eigenvalues for bound states, which I still haven't defined in this world, then the behavior is exactly opposite, which is not surprising, because remember that undressing, the undressing involves a bound state, which morally is just the inverse of the original eigenfunction. So that's why these two look very much alike. But of course, the problem is, what are these special values? And these things will be created will be used to create bound states for the scattering problem. So this is the first theorem. I said I will show you theorems. I will not discuss proofs, because the proofs are quite technical. So I have the essential quantity the essential free constant that I'm allowing is omega, and I'm now defining kappa to be this expression in terms of omega, and some just to simplify the notation, some c which is this. It doesn't appear here, but it will appear on the next slide. So I have the minimum of 1 in omega and the maximum of 1 in omega, and I'm going to treat this system of linear equation, linear over the semi-fields, for a potential that has finite support. And that is absolutely crucial. I mean, there are different parts in all the proofs that break down if the support is not finite. And then you can show, and this is not too hard, that this system has 2 different types of solutions expressed in this way. Now, you might say that I'm cheating, because I'm actually using what is really, at the end of the story, these u's will be the initial condition. And I'm using 1 time step before the initial condition. But of course, there's an explicit expression for this, because the ultradiscrete KdV equation is time reversible. So if you have the initial condition, you could always pretend, of course I'm cheating a little bit, but you could always pretend that this notation is just shorthand for this complicated expression in terms of the initial condition. So it's pretty complicated, but it's uniquely defined. And now the statement is that these 2 functions are solutions to these 4 equations if the omega in the equation or in the solution is large enough. And now the problem is to determine how large it should be. So there's some minimal value that you have to determine. Now, as I said, these are linear equations in the sense that if you take the maximum up to shifts of these 2 solutions, you again get a solution. So by combining these 2, the final statement is that this is a solution, actually it's a 2-parameter family of solutions to these linear equations, involving a free constant is simply a translation, and this omega, which is basically a spectral parameter. And these are generic eigenfunctions for the free direct scattering problem. Now, how do you determine the minimal size or the minimal value of omega? So this is what I call omega max, which will be actually the fastest soliton. This will be the speed of the fastest soliton in the initial condition. And again, this took years to actually clean up, but there's this, even now, rather mysterious function x. That's actually the motivation to call it x, which has 2 alternate forms, and simply that is because of mass preservation in the system. If you see that the mass in the system is preserved at all time steps, then it's easy to show that this and this it's exactly the same. And again, I'm cheating a little bit. I'm using very compact notation for very complicated objects. So I need the update and I need the downdate of the initial condition. But it's local in, well, the equation itself is not local. Everything moves from left to right. So it would be a bit much to ask for completely local things if you're starting from a non-local object anyway. Yes. So it's local up to a point. So then there's a rather interesting theorem which says that actually the value omega max I'm after is the maximal value of this object that is defined in this way. And then the maximum of 1 and omega max is the speed of the heaviest or the fastest soliton in your state. And this is an example. I mean, this initial state will come back afterwards. So this is the kind, I didn't want to make things too involved. So I chose an initial condition over the rationals. And so if you start from this state and you do the calculation, and you get this plot. So the red dots are the initial condition, the blue dots is the value of x. And you see you have these plateaus at value 3. For continuous KdV, the spectrum for the scattering problem is simple. For discrete KdV, it is simple. But of course, you can imagine in the discrete world, just as in the continuous world, you never have two solitons with exactly the same speed. But of course, you have a vast amount of solitons that at the ultradiscrete limit will have the same speed. So it's physically, it's already clear that the spectrum for this scattering problem can never be simple. And that's actually visible. It's invisible here. You have at least two separate plateaus with maximal value for this x, but actually there are two solitons sitting here. So it's not visible in the plot for x, but there are actually three solitons with the same speed here. And then there's a neat proposition how to discern on any given state whether there are solitons that are going to be asymptotically separate from the background, and that is a local criterion. And in the conclusions I'll come back to this, but that's not important now. So this was theorem 1. So now we know what omega max is. You calculate this x function, you see where its maximal value is, and then you know that if you're above that maximal value, then this thing will be a two-parameter family of generic free eigenfunctions for the direct scattering problem. So, okay, what about bound states? Again, kappa and c are defined in the same way. You can show that if the spectral parameter in the linear equations takes exactly the value omega max, then the minimum of these two is also a solution. Now, the proof of this is rather tricky because the phase constant is no longer free. The soliton has to be at a very specific place in the state, and so the bound state has to take a very specific form. So, of course, it is not unique in the sense that the spectrum is not simple. So if you have multiple solitons with the same omega max, then you will have as many bound states. But if you choose the phase constant exactly right, then this is the only solution that has that property. And this MT is basically any position within the block where this x function takes its maximum value. And you can prove that actually the relation doesn't. Up to a gauge, it's basically the same relation if you choose a different position within the same block. And this is what I will call a bound state eigenfunction in the ultradiscrete world. And now, for all practical purposes, the direct scattering problem has been solved. And then you have to define a dressing transformation, first of all. And that, luckily enough, was already known in 2009 by a student from the Graduate School of Mathematical Science at my university. And the dressing transformation works on the tau function. So this is the dressing transformation, and it's exactly what you obtain by doing an ultradiscrete tau function with a generic free eigenfunction. So this was the generic free eigenfunction. Add it to the tau function, do some manipulations, and you have the result that was shown by Nakata-san in 2009. The dressing transformation is pretty tricky. It's almost trivial to show that if you go to the new potential variable, u tilde, which is now defined in this way, that you increased the mass of the initial state by omega, that is the new eigenvalue you add it to the discrete spectrum. But the shape of the dress state is very, very hard to describe without doing the actual transformation. Now, how do you do undressing? Because you could say, well, simply flip the eigenfunction and in a sense, in the semifield, divide by the eigenfunction. Yes, but remember that the original eigenfunction was defined in terms of the first potential. Now, if I want to undress a new potential, I want to have an eigenfunction defined in terms of the new potential. I don't want to be defined in terms of the target. So yes, there is an expression, but it's completely useless. So this doesn't work. So this requires quite some careful thinking. And you can, first of all, if you cheat and use information that you're not allowed to use, then it's very easy to see that it actually does what it needs to do. Yes, but I'm cheating because I'm using information that in a generic undressing setting is not available to me. I already know where I'm going. Yes? But if you allow some level of cheating and you see that you take off exactly the right amount of mass, and the undress state is very simple. It's actually, you take the update of your state, you take the downdate of your state, and you cut out the piece in between. Piece that is common, and that is simply the undress state. So it's even by hand, it's very simple to calculate. But this is useless because I'm using information that I'm not allowed to use. So how do you solve that? Well, I'm sort of running out of time, so I'm going to cut this short. There is a way, and this is basically the hardest part in all the proofs. You can construct an alternative expression for, in a sense, the inverse of the eigenfunction, the free eigenfunction that you used to dress the state, which is now a bound state for the dress state. There's an alternative expression using only information on the dress state, which looks like this. This is also a solution to the scattering problem, which is related to the original one I showed you by this very simple relation, which is exactly the ultradiscrete equivalent of the relation that we had in the discrete KdV case. So this is rather technical, but there is an explicit formula, an explicit expression for the bound state eigenfunction for a dress state that will do the correct undressing. So there is now a uniquely prescribed way to dress an initial state and then take off all the information that you added without perturbing the rest of the spectrum. So that's the most important result. And then you simply go through the algorithm. So you start from an initial condition and you start undressing. First with the fastest soliton, then with the second fastest, with the third fastest. Some of these might have the same speeds. And you have to record two sets of information, all the solitonic speeds and these phase parameters that determine the exact position of your bound state on the lattice. So you have a set of n of these pairs of information. You could have the splitting points or the defined maxes, that's irrelevant. And then since your solution has finite support, it has finite mass. So after a while, you will necessarily obtain a state where there are no solitons left. Now the nth step. And well, this is an example of an undressing. So this is the original state that I already showed you the evolution of. And this is it's a bit small perhaps, but this is the plot of the x. It's just the plot that I showed you. And so this is soliton mass 3, and you choose a bound state that is somewhere here. That is this position 17. Yes. And then you calculate the undressed state, which is this one. That's the B state. You do exactly the same thing, calculate x, and you see that, well, in this region, there were actually two solitons because there's one left in the same region. And so you can choose this one, which is this 34 divided by 3. This is the position 11. And you keep doing this up to the point where there are no solitons left. As I said, there's a very simple local criterion that tells you if there are solitons or not. And then you have all this information. And then the important fact is that if I go back one slide, this thing, the completely undressed state without any solitons, the time evolution is trivial. This will simply move at speed 1 towards the right. So if you write this state as bi0, then this is the tau function that describes this right translation. And if you know the tau function, you know the U form. And then you use the dressing transformation that I described earlier on the tau functions to actually dress them in reverse order. So you start with the slowest soliton and you put them back at all correct places because you know exactly where all these bound states were situated in the undressing, the way to solve the Cauchy problem. Yes. So this is, I have to explain what this plot is. This is exactly the same. This is the initial condition I showed earlier, where I only show you evolutions at steps of 10 time steps, and I shifted back by speed 1. So I'm a moving reference frame that moves at speed 1. So the background at the end doesn't move, because otherwise everything moves out of the picture. So I decided to be in a moving reference frame with speed 1 moving to the right, and you see the 3 solitons with speed 3 coming out. And then it takes time, but you see that there's some wiggling, and then there's another soliton coming out, and then yet another one, and then this bit will simply move at speed 1. So these are these speeds. These were the speeds: 3, 3, 3, 4/3, a half, and then the background that moves at speed 1. That's exactly what you see. And then I'm almost done, and my iPad froze. Okay, so these are now the conclusions. So there is a method to solve the Cauchy problem over the real numbers for ultradiscrete KdV, and hence also for the VBS, that is, well, morally equivalent to the inverse scattering problem for discrete and continuous KdV. And again, I'm taking chances here, but I think it has to do mainly with the algebraic properties of their integrability, because you can only do algebra in the ultradiscrete setting. I believe that the same scheme should work for ultradiscrete versions of the Toda equation, maybe the Voltaire, all these equations should have a similar structure. So probably you can do exactly the same thing for other systems. It's not unique to KdV. But the interesting connection is I have 2 sets of, I didn't stress this because I had to cut some slides, but basically you have one set of constants of motion, the soliton speeds. All these omegas were preserved. You have these phase constants, these phi maxes. They play the role of the left normalization constants for the eigenfunctions, and they evolve linearly. I mean, I didn't stress this, but you know, the equations I showed you will simply phi max plus CT or minus CT. So I now have action angle variables in the original KdV inverse scattering sense. How are these related to the rigged configurations? Now, if you remember the construction of the rigged configuration this morning, Kuniwa-sensei's talk, you go the other way around. You start with the smallest solitons and then work your way to the largest soliton to obtain this information. So that relation seems to be very, very complicated. However, in the slot decomposition, you go the other way around. In slot decomposition, you do first gain information on the fastest soliton and then work your way down to the slowest one. So I think if there is an easy connection between the action angle variables that we use to solve the Cauchy problem for the VBS stem and something that has meaning in combinatorics, then probably the best bet is to find a link between these scattering type action angle variables and slot decomposition. Thank you very much.
Thank you very much. Thank you very much for the talk. Are there any questions?
Thank you, doctors. And so you introduced the ultradiscretion of Lax pair.
Yes.
So is it possible to consider some backward ultradiscretion of UD quadruple Lax pair? Is there some meaning of this backward transformation?
It will simply be the original discrete Lax pair, I think. The only meaningful one will be.
You mean possible to return to the or discrete one? Or
yes, because I said the two of them are simply ultra-discrete limits of the original discrete Lax pair.
Mm-hmm.
One of them is the update of the spectral problem, but it's the same. If you go backwards, it will be again the same equation. And the fourth one is simply a non-trivial combination of the discrete equations, which you then ultra-discretize. I mean, the ultra-discrete equations can't be combined. So you basically have to take exactly the right combination of the discrete equation in the Lax pair and then take the ultra-discrete limit.
Mm-hmm.
And then you get equations that actually make sense.
Okay.
That
That's
is probably a non-algorithmic step. It involves luck. I think.
Thanks so much.
I think it's safe to say that almost everybody has their favorite integral system. And KdV has been hugely prominent in our lectures. But another famous one is the cubic nonlinear Schrodinger equation. Is it the case that people say, well, you work through the same details and you're going to get everything's going to work out nicely, or no?
I'm glad you asked. Because basically your question, first of all, boils down to another question. What is a nice version, a nice discrete version of the cubic nonlinear Schrodinger equation? There's, of course, there are fully discrete versions of Slavic. There's a nice paper by Yuri Suris, where he actually gives 3 or 4. But honestly, they're very, very complicated systems. And 1 or 2 of them might be useful in numerical computations, but even that is very, very involved. So going that route is not going to work. There is another version of, well, another very interesting discrete version of NLS, which is not very well known. It appears in one of these. There was a long series, 7 papers by Jimbo Miwa Date on discrete soliton equations. And the equation is in number 4 of that series. It's not very well known, but it is, with a little bit of work, it actually becomes sign-free, the equation. So that's encouraging. But unfortunately, the time evolution is very, it's completely skewed on the lattice. So it's not, it doesn't evolve in a nice direction. Computationally, it's quite involved. So yes, the equation itself can be ultradiscretized, but probably, I haven't looked at it in detail, but probably you will have to transform it a little bit so that it has a nice evolution. I mean, it's sort of difficult to impose boundary conditions or an initial boundary value problem that will have a nice evolution that might be useful. So that's the tricky bit. Algebraically, it's clear that it's a nice equation, but the initial value problem, it's not clear how to define it in such a way that it actually makes sense in the algorithmic limit. So the short answer is I don't know how to do it. Well, I can't claim to speak for other people, but yes, probably nobody knows, I would say.
Thanks. Other questions or questions online, maybe? Do I have a quick question?
Yes.
So you talk about the remaining stuff that is left after the solitons.
Yes.
So does that also interact with the soliton in some kind of nice, well-defined way? Is there some scattering for that?
Thank you for asking, because as I said, there's this nice local criterion that allows you to decide when there's a soliton or solitons that separate asymptotically. I mean, of course, that statement also implies that there are solitons that do not separate. So you have solitons with speed 1, with mass 1, that are basically stuck in this background. So yes, so first of all, you would expect non-trivial interactions, but actually everything goes through, as in the case of the continuous KdV equation. There is a non-trivial phase shift of the solitons when they traverse this background that moves at speed 1. And actually, just as in mathematics, I mean, if you look at the phase shift, there is no difference between solitons embedded in the background or the background itself when you look at the interaction properties. It's exactly, you can pretend that these solitons are basically background solitons.
And the background keeps its shape under
Yes.
interaction.
Yes.
So
Well, not while traversed.
No, but
Yeah,
after,
but it comes
after,
out
I mean, after
as it was
interaction.
before, but simply shifted backwards by 2 steps.
So this is like a whole, like a large set of new particles, if you wish, right?
Yes.
Any
Yes.
shape of the
Yes.
background
Yes.
is some definite
Yes.
asymptotic
Yes.
object. Yeah, thank you. If there are no other questions, let's thank
Thank you.
again.